Okay, it's a pleasure to welcome Anurag to our seminar. Anurag recently joined Harvard University, actually this January. Before he got his PhD from Singapore, the National University of Singapore with Raul Jain, and then did 2 postdocs at IQC in Canada, and then Simon Institute at Berkeley. He's an expert in many topics, including quantum communications, quantum many-body systems, and quantum complexity theory. Actually, yesterday when Chanter was giving his talk on quantum maxcut, we saw one of his recent results. He's also expert on quantum many-body systems. For example, his recent result on area law for 2D frustration-free systems is something that I wanted to highlight. And of course, his and his collaborators' new breakthrough on no low energy trivial states that is going to talk about today. Yeah, Anurag, the stage is all yours. Take it away.
Thank you so much, Milad, for a really kind introduction, and nice to see everyone. It's also very nice that that I see some familiar names I have never met before. So that's very nice. Okay, so let me just share screen here. So it's a Jamboard talk, which means that I have already prepared some content here. It's almost like a whiteboard, but not quite. So what this means is that you're very welcome to interrupt me as many times as you want. And let's just fill in these pages with more and more stuff. I don't know how filled it is right now, but I mean, hopefully we can talk more carefully. And please interrupt and ask questions at any time. So as Milad mentioned, this talk is about NLTS Hamiltonians, which I'll explain shortly. It's a joint work with Nicholas Brookman from UCL and Chinmay Nirkhe from UC Berkeley. Both of them are moving, by the way, so affiliations have changed recently. But okay, so the central object that I'll be considering in this talk is that of local Hamiltonians, which I believe the physics folks would just know, and they probably dream about it often. It's a very standard object in physics. In computer science, it's rather, it can be rather new, but computer scientists can think of local Hamiltonians as quantum analogs of constraint satisfaction problems. So here I'll kind of try to provide both point of view. So imagine a collection of qubits. Let's say we have n qubits arranged in some manner. We don't require them to be on a 1D or 2D lattice or anything like that. Just put in some mathematical, like just some way. There is a rule which describes how they interact with each other. And that rule is governed by the Hamiltonian H, which I have labeled as Hn here because n is the number of qubits. So Hn, it's a Hamiltonian. It's a sum of a bunch of terms, which let's say there are m terms here. It goes from 1 to m. These local terms are what I've shown here in yellow. These are local interactions between these particles. This could be two-body interaction, three-body interaction, and so on. But there's some interaction that happens between them. And each of this term, it's mathematically a Hermitian matrix, and it only acts on a few qubits. And it, for example, H1 would act on these 3 qubits and act as identity matrix everywhere else. So it doesn't do anything anywhere else. We'll assume for convenience, which we can always do by changing the energy here and there, that all these HIs, these matrices are positive semi-definite. Their eigenvalues are all non-negative. And also the eigenvalues are at most 1, which sort of makes sense physically because we don't want, it doesn't make sense to have one small region of this collection of particles to interact much stronger compared to other ones. So usually the interaction strength is usually 1 or so at most, We can scale things there. So that makes, and we sum up these local interactions, and that makes up our Hamiltonian. And like any nice matrix out there, Hermitian matrix out there, a Hamiltonian has a spectrum. It has eigenvalues and eigenvectors. So lambda min is the smallest eigenvalue of the Hamiltonian, and that's called the ground energy. And the quantum states that correspond to the eigenvectors corresponding to this ground energy are called ground states. And as we go up, energy increases up to some maximum over here. Something very relevant for us in this talk is the notion of epsilon energy states. And by that I mean is all the states, basically the set of all states, including the ground state, whose energy is at most the ground energy plus epsilon times the number of particles. So notice the normalization, by the way, it's epsilon times the number of particles, not just epsilon. So that's important. I'm just going to call it conveniently as the epsilon energy states. So that's our setup. So there is a well-known result which I think it's worth writing down in this slide, which is Kitaev's theorem from 1999 or so, which says that if you're given a local Hamiltonian out there, computing the ground energy very, very accurately is very hard. And there's a term for that. It's QMA hard. It's like quantum NP hard. So it's even harder than, even if you have the power to solve NP complete problems, it's still hard despite that. So that's Kitaev's theorem for many, many years ago. But one thing that people often wondered, and that has become a pretty popular conjecture in quantum complexity theory, is the quantum PCP conjectures. I will not explain the terms PCP. It's not a drug. It's a mathematical statement. And the conjecture basically says that not only is it hard to compute the ground energy very, very accurately, it's also very hard to compute the ground energy up to a pretty large margin. That means there's some constant out there, epsilon, some universal constant, and some hard Hamiltonians, like some very complex Hamiltonians, such that for these Hamiltonians, determining the ground energy up to this large energy that I showed here as well is also very, very hard, quantum NP hard. So that's the quantum PCP conjecture. This conjecture sort of is probably the limit of how hard, I mean, if it's true, then it really says that it's extremely difficult to estimate the ground energy properties under the most free sort of assumptions you can imagine. But this conjecture stays open. There hasn't been a clear approach to it yet. So that's our setup: local Hamiltonians and quantum PCP conjecture. That's the starting point. And here's where the NLTS, or no low energy trivial states conjecture, comes in, which was posited by Friedman and Hastings around 8 years ago, which was one of the first serious attempts at quantum PCP conjecture, which I wrote down here, which is open. And the question was, well, this is probably a hard question to ask. So this was a seemingly simpler question than quantum PCP conjecture, and the question was, is there an epsilon, some universal constant, and a family of Hamiltonians such that all the epsilon energy states are complex, and complex in the following sense, that their quantum circuit depth is some big number. So there's a few things to parse here, I guess. I mean, how did complex come in? How did quantum circuit depth come in, and so on? But let me try to go through that slowly in this slide and the next. So complex basically comes in, complex sort of comes in from the same point of view as here. Quantum PCP conjecture sort of implies that these low energy states are complex in some sense. It's hard to use them to do anything useful. It's hard to make use of them to compute their energy. Because if it was easy, then things would not be QMA hard. QMA hard is the gold standard for complexity in the quantum world. But here, more specifically, Friedman and Hastings were interested in a very specific notion of complexity, which is quantum circuit depth, which is by now, as I'll talk about in the next slide, quite a popular notion of complexity for quantum states. So here's how it's defined. For quantum state psi, quantum circuit depth is defined as start with all zeros and apply whatever set of gates you want, quantum gates you want on all zeros for certain depth. That's the definition of depth. And then you should be able to output the quantum state psi. So, yeah, please. Sure.
In the rules of the game here, in terms of the gates that you're allowed to circuit, they only act pairwise and nearest neighbor, or what corresponds to a possible gate I can use in the depth?
Right. So you're allowed to apply any gates you want, any 2-qubit or 1-qubit gates, for example. Yeah, that's one canonical thing we can do, such that in each layer, gates have to commute. So of course, it's not meaningful to apply this gate and this gate in the same layer. This gate has to be delegated in the next layer. So any reasonable notion of quantum circuit, layer by layer application of quantum circuit is fine here. These results would also apply if, for instance, you were doing e to the IGT for some Hamiltonian. Also, I think I'm using the wrong. I mean, I'm just putting it in as a side note. If this question came in someone's mind, that even e to the IGT, which is sort of a time evaluation by a local Hamiltonian G, is also sort of like a circuit, not quite, but behaves like circuit for all practical purpose, like Lieb-Robinson bound and so on. So you could also ask this question using these things, and our techniques also apply there. But so any reasonable notion of low depth circuit is what basically is portrayed in this part. By the way, is my internet connection okay? Because I thought on Ivan's side I saw some signal getting bad, but I'm not sure if it was my problem or.
It's good on my side.
Okay, so is the internet coming fine? Okay, no, that's good. All right, great. So the moral of using this notion is that, well, high depth basically corresponds to long range entanglement, roughly. That's the sort of physics perspective, or high complexity from computer science perspective. If the depth is small, a constant, then usually you can't entangle this qubit with this qubit, they're far away. So low depth corresponds to low or short range entanglement in some sense. So that's one way to think about these things as well. So this conjecture was asking, in other words, that is there a Hamiltonian for which all the epsilon energy states are globally entangled? That's one way to propose this question. And the main result that we show is basically a proof of this conjecture. And in fact, our depth lower bound is roughly log n, which is better than what they conjectured in the original conjecture. So that's fine, but also this is the limit of what we can prove. For those who are aware of quantum complexity theory might know that there are not techniques out there, even classical complexity theory, there aren't any techniques out there to prove lower bounds on circuit depth beyond log n. So we are basically at the limit of knowledge of circuit complexity lower bounds. Okay, so once again, this is the conjecture. You want a Hamiltonian, a construction of a Hamiltonian, an explicit one, such that all low energy states for some constant epsilon require pretty deep depth, and that's what we'll talk about, how to prove that.
Just regarding your last point, if I allow free classical communication and I only count the depths of the quantum circuit, then we don't know how this, because of the last point you made, because even classically we don't know what's going to happen, right?
Yes, yeah. So if you allow free classical communication, even then it's not. For such, those are already pretty. Although there's a point though. I mean, if you were to send classical communication, you're going to do measurements, and measurements prepare mixed states. So maybe you could argue that condition on the measurement outcomes, there's a pure state, and that pure state should have high circuit depth. Maybe you could argue that way, I feel. Like, I mean, there might be an argument from the fact that classical communication requires measurement, and you could post-select on some outcomes here and there. But I'm not so sure.
But also you might lose the concept of locality. I mean, it depends on how you define the classical communications,
Right.
I guess.
Yeah, you're right.
Yeah.
Fair enough. Yeah, that's a good point. Okay. So I think let me again mention why quantum circuit depth in this conjecture, why not anything else? Why that was the question that they asked. And the main reason is the following. So let's look at the same quantum circuit that I showed you in the previous slide. That's the state psi. And let's say we are computing the following quantity. For a local operator O acting on this qubit, we're computing the expectation value of psi with O. Then I claim that this expectation value, which involves very large objects, psi is a quantum state on n qubits, very big. O is an operator, it's local, but still a matrix in a big vector space. Despite that, this quantity can be computed in 2 to the t time. That's the claim. So let's see why is that true. So if you look at this expectation value, you notice that this expectation value only depends on qubits in the light cone of this operator O. That's the only thing that's needed to determine this expectation value. So even if you threw away all these gates and made them identity, you'd get the same answer. And as a result, this computation, and so this number of qubits here are 2 to the t, because there's no geometry assumed here, like light cone can spread pretty fast. The computation is done on 2 to the t qubits, and on 2 to the t qubits, the dimension is 2 to the t. So the computation can be done in short time if t is small. So basically, one could imagine a procedure which is in fact something which is standard in many variational quantum algorithms, variational quantum eigensolvers, and so on, where we work with some ansatz, which is a low depth quantum circuit, and we try to estimate the energy with some Hamiltonian, and we keep trying till we get the energy low. So all these quantities can be computed in pretty short time if t is small, if the depth of the circuit is small. And that's one of the reasons why using low depth circuits, estimating the ground energy, computing energy is easy. So of course, if a quantum state with short circuit depth is close to, is a low energy state, then it's easy to determine ground energy using these ansatz. So if NLTS conjecture were false, if this statement were false, then we would have a disproof of quantum PCP conjecture, which means that quantum PCP conjecture implies NLTS conjecture. And also for other reasons, you might be interested in this question is because, well, if you like variational algorithms, then you might want to understand what is the limit of these algorithms. How well are these algorithms in approximating the low energy spectrum of a Hamiltonian or low energy states of a Hamiltonian. So that's another reason why quantum circuits are useful. Okay. So, all right. So I'll probably spend one slide trying to give an intuition of where to look for these Hamiltonians, these NLTS Hamiltonians. And a good way to start there is to, well, ask where not to look for them. So just to, and I'm ready to be criticized by physicists here, that in fact, the last place to look for these Hamiltonians is in our real world. And that probably is going to put many of you to sleep, but that's fine. And let me explain what I mean by that. You could ask, well, is a two-dimensional Hamiltonian a candidate for NLTS? And in fact, we feel in our bones that there are some Hamiltonians whose ground states, low energy states are complex. So for example, antiferromagnet or something like that. They are pretty complex. Ground states are so entangled and so on. So you'd expect that maybe even low energy states are low entangled. But let's say an antiferromagnet on a 1D chain or a 2D lattice, would those be NLTS? And turns out they're not. So here's a proof of that. And the proof goes as follows, that let's take our, let me do a little bit more drawing here just to kind of give this picture better. So let's say these small lines are the Hamiltonian terms, these interacting qubits, like this qubit, these are the Hamiltonian interaction terms. And we are given this full Hamiltonian Hn, and we want to estimate the energy of Hn up to epsilon. What I can do is the following. I can divide my lattice into many, many small squares. Each square has width 1 over epsilon. Basically, like, sorry, sides 1 over epsilon. And there are many, many squares here. It's pretty easy to check that the number of lines here are roughly, let me see if I can make it more precise. There were n qubits, so let's say this is root n and this is root n. It's easy to check that the number of lines here are roughly epsilon times n. Sorry, epsilon times root n, which means that the number of Hamiltonian terms that cross these lines are epsilon times n, or epsilon fraction of the total number of terms. So what you can do, for instance, is that you can throw away all these terms and you can solve these independent terms locally and find the ground state here. So just find the ground state of the Hamiltonian within this square, and that's your low energy state, which achieves energy epsilon times n with respect to the full Hamiltonian, because it only only creates excitation at these boundaries. It only violates the terms which live on the boundary. So we found an epsilon energy state, and to prepare this state, you just have to you just have to prepare the ground state here. A ground state is because there are only 1 over epsilon square qubits here, you can prepare that in some quantum circuit of some depth, 2 to the 1 over epsilon square. So this shows that these Hamiltonians cannot be NLTS. And in fact, the right place to look for the NLTS Hamiltonians, Hamiltonians with NLTS property, is a place where boundary is not small compared to the volume, where boundary is of same size as volume. In that case, you cannot make this argument for every epsilon. There'll be some epsilon where the argument will fail. And those systems, those Hamiltonian systems, they don't live in the real world. They live in, they do live in hyperbolic spaces and so on. But in fact, they very well live in what are known as expanded graphs. These are the graphs which, first of all, they cannot be embedded in any finite dimensional lattice. And the very nice property of these graphs is that they're very well connected. And they sort of behave like complete graph for all practical purpose. And any boundary, if you cut the graph into any two parts, then the number of cuts you made versus the number of vertices inside, it scales the same. So that's where we have to look for these Hamiltonians. So I can pause briefly if there are any questions so far. Okay, so seems clear. That's great.
You know how we have a question.
Yeah.
Okay.
Yeah, I cannot hear you.
Was it John? We can't hear the person who's asking question.
Sorry. Yeah, we were in the same room and there was some technical complications. Sorry about that. I just wanted to ask if this finite dimension argument that it never can become NLTS, like a very similar argument should go for any classical Hamiltonians with the same thing, right? For a similar classical statement. Is Is my understanding correct?
Yeah, that's correct.
Okay, okay, thank you.
So in fact, the classical Hamiltonians that show up in classical PCP theorem are also on expanding graphs. They don't live in
Right.
finite dimensional world. Yeah.
And these expander graphs, like you can basically, is it correct that you can basically assume that they're kind of like random graphs, like Erdős-Rényi graphs or whatever that has.
Right. So random graphs of constant degree give you expansion, good expansion.
All right, thank you.
But there are very nice explicit constructions as well, using some group theory techniques and so on, which work. Which also is the kind of things we use. I won't talk about those too much at all, actually, but those are called Cayley graphs, and the Hamiltonians that we use are based on Cayley graphs and so on. Okay, so that's one thing. That's some intuition about where to look for, where to not look for these Hamiltonians, and it sort of explains where to look for those Hamiltonians. And one of the excitements about NLTS is also that, well, NLTS Hamiltonian also lives on like a quantum PCP candidate. Any Hamiltonian that has to be a quantum PCP conjecture satisfying Hamiltonian has also to live on an expanding graph. And that's exactly what we see in NLTS property as well. So this kind of aligns well. Like conceptually, this seems to be the right question to ask. Okay. Now, next, what I'll tell you about is that, well, we sort of have a rough idea of where to look for these Hamiltonians. But now let's see, there's an elephant in the room, which is that how do I prove this kind of lower bound? Like, how do I prove these circuit lower bounds of this kind? So I'll tell you about the techniques that go into proving this. And in fact, the technique can be understood from two very simple examples, which are sort of counter arguing examples. So one example is, let's say, a collection of plus states. Another example is the cat state. So we know that a plus state is pretty easy to prepare, right? It requires depth 1. But a cat state requires lots and lots of depth to prepare. You can't prepare it in a constant depth at all. So it seems right, it does seem intuitive, but how do we formally prove it? And the proof of that comes from looking at these quantum states and asking what happens if I measure these quantum states, and looking at the distribution that comes out of it. So let's say I measured the plus state in the computational basis. What I'll get is a bunch of independent random bits. So I'll get a uniform distribution over all n bit strings. And that's what I have portrayed here in the best possible manner over here. So imagine this is the space of n bit strings, and there is a uniform distribution over it. That's what you get from here. On the other hand, if I measure a cat state, I get either all zeros or all ones. So I get one string over here, which is all zeros, and I get another string over here, which is all ones. And the difference between the two, among all differences, is that in this case, this and this part of the distribution, that's where the distribution is totally located, they're really far apart. But in this case, there is no way to divide up your region into parts, two faraway parts where the distribution is mostly located. So basically, what we see is that a low depth quantum state, it's pretty well spread. A high depth quantum state is sort of clustered like this. And that's the difference, which also is very important, very clearly used in classical computing. So in classical computer science, when people want to prove a lower bound on the circuit depth to prepare a distribution, they kind of argue this way. So here's the first, here's a circuit lower bound method that works, that we will be using, and that's sort of a theorem that summarizes what we just discussed. Sorry for the very technical looking thing, but let's go through it slowly. So let's say I'm given a quantum state psi that was generated by a unitary on all 0 states or something with depth T. That's the depth of the circuit. And let's say I measured this state in the computational basis and I got a distribution over strings over the measurement outcomes. And this distribution might look something in the space of n-bit strings. It might have some form. Then the following holds that if you can find two sets, S1 and S2, which are relatively far apart, their distance is d, and at the same time, the distribution d gives a lot of mass here and mass here in probability, then t should be large. More precisely, t is at least log of the square of the distance over n is the number of particles, n is here, times log 1 over this crazy number. Precise thing doesn't matter. But for example, let's say if this was 1 over 10, this was 1 over 10 probability. I mean, d of S1 was 1 over 10. This was 1 over 10. Then we would get roughly log of 100. I guess in short, we would get t to be roughly omega log d square over n there. So basically, if it so happened that the distribution, it was giving a large 1 over 10 probability on two set of strings, whose distance is at least square root of n, more than square root of n, then you'd see a circuit lower bound. So that's the main circuit lower bound toolkit that we use. There is another, the opposite perspective, just to give an intuition, that a distribution that is not generated this way, a distribution that is generated by a low depth circuit, it has this very nice property, which is the usual central limit theorem kind of property, which let me just sketch it in this part. So concentration is opposite of this. For example, if you toss n coins which are independent, then in Hamming weight, you see that they concentrate within the average up to a standard deviation of root n. And this root n and this root n, this d square over n, which means d should be at least root n, are exactly the same thing. So to prove the circuit lower bound, you have to see your distribution going far away beyond root n distance. So that's sort of the toolkit. Now the question is, well, okay, great, this is a toolkit that's useful, but how do you use it? Like, where do we look for a Hamiltonian whose low energy states have this property, which seems like a whole bunch of statement to go through. Luckily, in the world of quantum error correction, we already have such things in place, at least for the ground states. So I'll spend some time convincing you that quantum codes are great NLTS candidates, especially good quantum codes. So for that, let me spend some time recapping what quantum codes are. If you know what quantum codes are, it's the time to sleep for 5 minutes. And let me just go through that. I'll do quantum codes discussion from Hamiltonian perspective, just to put things in place already. So, well, let's first talk about what classical codes are. A classical code is basically a classical Hamiltonian in which our Hamiltonian terms are this term where z to the a is basically this over here is, for example, if a is 1, 0, 0, then z to the a will be z1 tensor identity. So a classical code is pretty much a classical Hamiltonian in which we penalize if z to the a doesn't look like identity for a bunch of a's, where a comes from some set pz, which are parity checks, some n-bit strings of low Hamming weight, which are the, maybe I should write it down here. These are parity checks. Usually parity checks are denoted by h, following Hamming notation. Unfortunately, we are using h for Hamiltonian, so we have no choice but to call it p. So Just recall that whenever a z to the a acts on a string b, a string in the quantum notation, we get a phase of -1 to the a to the b. So if whenever a dot b is 0, that means a string b satisfies a check a, then we see that b is satisfied by z to the a, or b gives a 0 here. So the ground space of a classical code is basically the set of all strings which satisfy a dot b equals 0 for all a that comes from the parity check, or this is basically the set of code words of this parity check matrix. So that's this is just a unusually inconvenient way to write a classical code, which is by calling it a Hamiltonian and so on, and a parity check just becomes a Hamiltonian term. So I hope this is, I hope this part is not too confusing, and hopefully it was clear, and please ask me questions if this didn't make sense. More importantly, a quantum code is basically two classical codes put together with some constraints. So a quantum code, in particular a quantum CSS code, is a sum of two classical Hamiltonians, one in the z basis and one in the x basis. So in the z basis, we have a parity check which we are calling PZ already. In the x basis, there's a parity check PX. And here in the z basis, z to the a checks the parity. In the x basis, x to the b checks the parity. We often like things to commute. Commuting is good. So for that, we also want hx and hz commute, which amounts to saying that a dot b equals 0. That means b and a are always orthogonal to each other, which means the string b's are in fact code words of a. So that's something which is used. So in fact, if you think about it, because if I want to have a local Hamiltonian, then I want PZ to be low Hamming weights, PX to be low Hamming weights. But because B's in PX are already code words of A because of commuting condition, individually HX, HZ is a pretty terrible classical code. Its distance, for those who know, its distance is a constant, just the weight of Z part, weight of the X part, and vice versa. But when combined together, they form pretty good quantum codes. So CSS is well known. It's for Calderbank, Steen, and Shor. All right. So this was a very quick discussion on what quantum codes are. If this was too algebraic, then a picture is coming soon. And hopefully this picture will be helpful. In fact, this picture will be very helpful to us, given our discussion about how to prove circuit lower bounds. So let's look at this HX code, the classical code HX. And let's again plot all the strings in our space of strings that are the code words of HX. It turns out, for the reason that I quickly mentioned earlier, that the code words of HX have the following form. Either they are small, low weight code words, or they are large weight code words, which means that all the code words are sort of clustered in the following manner. So for instance, if this was, I think all zero string was somewhere else, but never mind. If this was all zero strings over here, then you have this cluster of very low weight strings, which would make for a terrible classical code. But the nice thing is that they're sort of far apart from each other. And what really matters for quantum error correction is not what is the distance of the classical code, but rather what's the distance between these clusters. And that's the distance of the code. And the way to think about it is that if an X error happened, X error could stay within this or take you far away, but staying within is okay, because that's not really where you encode the information. In a similar manner, we have the X code, the HX, which again has the same picture. It has, for instance, the all zero strings here and a bunch of low weight code words here, but then they're clustered, and the distance between them is what really matters. And the minimum of these two distances is the distance of the combined quantum code, where dist is just the distance of the code. This is the size of the errors that can be corrected by this process. So a very nice approach was developed by Eldar and Harrow around 6 years ago in their attempt to prove NLTS. And what they basically argued that, looking at this picture, it should be clear by now, but the main point was that quantum code words of such a code where the distance is large have high circuit lower bound. And that's simply because a quantum code word is a quantum state psi. If you measure psi in the z basis, you get strings in the green part. If you measure psi in the x basis, you get strings in the green part over here. So they said that, well, take any quantum code word like that, and let's say the distance is at least root n. Then what happens that, well, psi is a quantum state, it outputs a distribution over these strings, it outputs a distribution over these strings. If these distributions were well spread in this set, so for example, let's say in the z part, the distribution had some mass here, some mass here, some mass here. In that case, what we've done is that we have sort of created a situation like this over here, where there are distributions which give high weight at faraway strings. And as a result, we would use this circuit lower bound technique. But the trouble is that here's a bad scenario, that maybe psi outputted a single string over here if you measured it. And in that case, there's no way the distribution spreads across different clusters. But then they argued, Eldar and Harrow, it was a really cool observation that, well, you can bring in uncertainty principle, which basically says that you cannot be concentrated in z and x basis at the same time. That means if you took a quantum state and you measured it in the z basis, and let's say the answer was all here, in the x basis, there's no way you can be concentrated here. You have to be spread all across. And then you get a circuit lower bound, because at least in one of the two bases, you have to be well spread. So this was their argument for proving that quantum code words require large circuit depth. They proved a stronger statement as well. They proved what they called NLTS theorem, which was not really low energy, but low error. That means the states that are obtained from quantum codes by making small errors to them. So that's how they got their result. So in our case, and now I come to the main technique here. I have 15 minutes, which is, I think, pretty good time to finish it off. So our main contribution is basically to show that this kind of property holds not just for quantum codes, but also for all low energy, like approximate quantum codes of a good code. So what's a good quantum code? It's a quantum code which has distance very large, roughly n, and the rate, that's the number of encoded qubits, is also very large. There are nearly linear number of encoded qubits. So these codes were recently constructed in the breakthrough work of Panteleev and Kalachev from last year, and a very nice simplification was obtained by Leverrier and Zimmer this year. So our main technical result, which uses these codes, and because someone asked this question earlier, these are based on Cayley graphs. So these are quantum codes constructed on expanding graphs of some form. So our main technical result is that if you look at the approximate code words of the X and Z part, then they form the following picture. All these approximate code words sort of form a cluster similar to this picture that you saw here. But what's key is that, which was the main bottleneck since the work of Eldar and Harrow, which is the main contribution of this work, was that these clustering property will happen, but you will have new clusters. Instead of these 3 clusters, you will have lots and lots of more clusters, and the distance between them will still be large. And the same happens in the Z part and the X part. And once you have that, this again, just to highlight this a bit more, this picture is a consequence of expansion properties of the Cayley graphs. So we show that these approximate code words satisfy this property, And then what we use an idea similar to Eldar and Harrow, which is to bring in uncertainty, but it's a stronger idea, which necessarily requires linear rate, which basically says that if you were, again, intuitively same thing, that if you had a quantum state psi, which was a low energy state, and you measured it in the z basis or x basis, you would get a distribution, and there's no way for the distribution to be located here or just located here. In one basis, it has to spread a lot. And that leads to the circuit lower bound. So that's pretty much the high level view of the techniques. And now let me finish this with a collection of open questions, which we don't know the answer to. It'll be great to figure those out. So let me go from bottom to top. So we show that these good quantum codes, which have linear distance and linear rate, in particular, these specific quantum codes have this nice property, which seems to come from expansion. But what we don't know is that, is it possible that any good quantum code that could be constructed in the future, which may be of different nature as this one, are those NLTS as well? And this is a pretty nice question for the reason that a proof of this will somehow point to the structure needed to create good quantum codes, like expansion of the underlying interaction graph or so on, which you don't know how to do. So this is a nice question, probably more tractable. Another question, which is even more tractable probably, is the fermionic NLTS conjecture of Hastings and O'Donnell, which was proposed very recently in 2021. And the conjecture asks a related question to NLTS, which is that, well, if you have a fermionic Hamiltonian, which I have little understanding for, so let's put a wiggle here, which looks like summation of sum over some terms and fermionic operators. Can we find Hamiltonians whose all low energy states are not fermionic Gaussian states or low depth circuits on fermionic Gaussian states? So that's another nice question which potentially can be solved given this technique. A very interesting and a very difficult question is this one. That's the one top, and let me call it a practical quantum PCP. So the two main techniques that we have right now to simulate quantum states, they are based on quantum circuits and stabilizer representation. These two classes of quantum states are easy to simulate classically, and you can compute expectation values easily. So this question asks, is there a Hamiltonian for which all the low energy states are not only deep circuits, require deep circuit, but also they are not stabilizer states. In fact, they are far from it. That means they require lots of stabilizer rank. This is not true for this Hamiltonian because the code words themselves are, the code words of CSS code themselves are stabilizer states. So that's not the right thing. So this requires us to look for much more interesting Hamiltonians. And if those Hamiltonians would basically be the ones which we cannot simulate at all using any technique available to us. And this is probably a very hard question because we have very little technique available for stabilizer rank. For circuit depth, we have exactly one technique that I talked about here. That's the only one. But in fact, for stabilizer rank, we have zero, pretty much. So that's something which would be very, very interesting to make progress on in the future. And with that, I'm basically done. Thanks for listening, and have a good.
Thank you, Anurag.
Thanks.
Thanks for the great talk. Yeah, let's ask questions.
Yeah, please grill me.
May I start with two quick questions? Everyone warms up and asks questions. First of all, about the last point here on this slide, do we know that classically, if I choose some random LDPC code, whether this is satisfied or not?
So NLTS. So is a question whether if you choose a good classical code, is it like PCP or something?
No. So I'm thinking about defining NLTS for classical circuits, and then asking whether if I choose a good classical code, for any good classical code, such NLTS works or not.
So circuit depth would not be the right notion for classical Hamiltonians, because the classical Hamiltonians solutions, the ground states are always bit strings, and they're always just depth one circuit. But actually, what you pointed out is kind of connects to a very interesting result in classical computer science, which is that roughly any good classical LDPC code can't be approximated using sum of squares algorithms. And sum of squares is like, just like quantum low depth circuits are sort of, for us, a family of ansatz. Sum of squares is also an analogous thing for the classical code. And there they can prove that, yeah, good classical codes can't be approximated by the sum of squares algorithms. So it's of similar flavor. And this could be classical LDPS. So something like that would be very nice indeed. And that's like the analogous question here, which you don't know.
I see. And the other quick question is about the AMS and Elder's result. Why it doesn't capture an LTS? I missed that point. The previous theorem by Harrow.
Yeah.
Why it doesn't capture the NLTS? What's the barrier?
So the barrier, which it was a crucial barrier actually, which was that their result was true for quantum codes, which was ground states only, or states that are obtained by applying Pauli errors on quantum codes, which are low energy states, but they're not all low energy states. They are a subclass of low energy states. So that's what they call them, low error states.
I see.
Yeah. So that was something which was part of the technique. And they also proved a very nice result, which was quantum locally testable codes are NLTS. Unfortunately, we don't know any such codes, like of linear distance, but there are no such codes. So, yeah. So
even classically, that was just proved a few months ago. So,
yeah, that's a good point. But the thing is that for this theorem, they just wanted one encoded qubit and linear distance. But classically, one encoded bit and linear distance LTC is sort of trivial. It's just a repetition code on an expander graph, basically. So just put expander checks and that works.
I see.
Yeah. So even we don't know a quantum analog of even that construction, which is shocking to be honest. But yeah.
Okay. Now questions.
Yeah.
Other questions.
Yeah. Please take revenge on my really boring talk. Just shoot questions.
I have a question.
Great talk. I really liked it. I'm in one of the big rooms. I have several questions actually. So one thing is, when I think about the classical PCP theorem, as you said, like it's usually like, it usually talks about these NP-hard problems, like the max KSAT or something on these like rather random graphs, I guess. And I was wondering, like, would you think that, for example, if you have a antiferromagnetic Heisenberg model on a expander graph, like, do you think that would have a quantum PCP or at least this kind of NLTS feature? Or...
that's a great question. Yeah, I mean, I feel my instinct is that definitely antiferromagnet on an expanding graph would be NLTS, but it's not clear how to prove it at all, because our tools for circuit lower bound sort of are of this kind.
Right.
And it's very hard to characterize the low energy states of Heisenberg antiferromagnet, but it would be great to prove that those are NLTS. In terms of quantum PCP, are those quantum PCP? Also, I believe they are, but we don't have a quantum PCP theorem for any Hamiltonian, so I feel that would be much harder to prove.
I see. Also, so this could be kind of tangential, but for example, it seems like if we think about a expander type graph, but like that is restricted to a bipartite case, and then like if you think of the anti-ferromagnetic Heisenberg model, for example, like we can definitely do quantum Monte Carlo on it. And yeah, I come from like condensed matter, so like I've been doing that kind of thing, and like I know it mixes fast.
Right.
And also, but like in that case, it is really just sampling the Z basis states.
Mm-hmm.
And does the Z basis sampleability like have anything to do with these kind of circuit complexities?
Right. So yeah, so if you have a bipartite antiferromagnet, then you can do this flip. You can flip one side and make it sand-free and so on, right? So yeah, that's a good point. In fact, a few months ago, I was trying to attack NLTS using bipartite antiferromagnet. Didn't work, and probably that's the reason that you mentioned, that maybe they're just easy to sample from those distributions. And so just to ask now, to shoot the question back to you. So what is the depth in which those algorithms work?
You mean like
Some sampling algorithms for bipartite antiferromagnets.
computational complexity? You mean like
like depth? Yeah, sure. Computational complexity as well.
Right. So like typically, you know, physicists just believe that they're all inverse polynomially gapped systems.
Mm-hmm.
So you just need to fix like the temperature to a polynomial size, and then the quantum Monte Carlo basically like maps the quantum system into a polynomially larger system just by a polynomial factor, and then like you're doing kind of a Markov chain on top of that, which if mixes fast, like gives you a good sampling of the Z basis states. So like, you know, if all of my assumptions are correct, it's kind of like a polynomial time algorithm, but like in PCP or something. But of course, like these assumptions are everything that physicists believe, but it's I don't know to what extent these are proven rigorously, and I believe not. So like I guess, you know, those are like the harder parts, of course. But that's my understanding of how these things work.
I see. Yeah, yeah. It's if those are sort of sampleable, then I feel they might be not NLTS. I mean, just a feeling, but I don't have a proof, of course.
I see. Thank you. Okay. Yeah. Actually, I have another person. Yeah.
Can I ask you just a related question? Like, how would this NLTS conjecture be still true if you consider stochastic Hamiltonians on these graphs?
Right. Yeah. So that's a good question. If you restrict it to stochastic Hamiltonians, one could ask this question, and I'm not sure if.
So your Hamiltonian is not a stochastic already?
So it has X and Z parts. Is it stochastic?
Yes, but you add all the X terms with a negative sign, right? So you have Z terms and then minus a lot of X terms.
Right. So is this stochastic already? Like
I think so.
Oh, okay.
That was stochastic.
Yeah.
Okay.
So it's already a stochastic. Yeah.
Oh, right. Yeah. The ground space, the CSS states, right? So
yeah.
All plus states there. Yeah. So there you go.
Okay, I guess stochastic Hamiltonians is enough to prove this.
Yeah. Seems. Yeah. Based on the sign. Yeah.
And Benjamin, did you have a question?
Yeah, I did. As I understand your explanation, this Elder and Harrow theorem doesn't capture NLTS because you only that one only considers states which differ from a code word by some poly errors. And so, what are the approximate code words you're talking about in your proof?
Oh, so there are any quantum states psi, which has low energy with respect to this Hamiltonian.
Okay.
So the issue is that to get to those states, you may have to make lots and lots of errors. So that's why you cannot be captured by the Elder-Harrow technique here.
Got it. Okay, thank you.
And in fact, also there could be superposition of many such errors. So
Other questions? Actually, Anurag will be around for another half an hour or so, but if there's no other question, let's thank him one more time
thanks.
for the great talk. And then, yeah, I guess we can stop the recording, and then we'll have some informal discussions for whoever